This video on related rates will cover these four problems, which are very common in testing. And if you want to skip forward to one particular type of problem, the video is indexed to the following times. In order to do related rates, you need to be able to do implicit differentiation. If you need to review that, click on the link in the upper right-hand corner. In this problem, a 12-foot ladder is placed against a wall. The bottom of the ladder is being pulled away from the wall at a rate of 1 foot per millisecond. How fast is the top of the ladder moving down the wall when the bottom of the ladder is 8 feet from the wall? Well, the ladder is forming a right triangle, with the bottom of the triangle being x, the part against the wall being y, and the hypotenuse of the triangle is 12. Using the Pythagorean theorem, we have x squared plus y squared equals 12 squared. And 12 squared is 144. And in order to proceed, we need to use implicit differentiation to differentiate this. And when we do that, we get the derivative of x squared is 2x, and we need to differentiate this with respect to time. So this is going to be dx dt. To differentiate y squared using implicit differentiation, we would have 2y dy dt. And on the other side, the derivative of a constant is just 0. We now have to solve for dy dt because we're trying to find the rate at which the ladder is moving down the wall over here. So we need to move everything else to the other side of the equation except for dy dt. So first I'm going to subtract 2x dx dt and move that to the other side. The next thing is to divide both sides by 2y. Once we do that, dy dt is on its own. Then minus 2x divided by 2y simplifies to be minus x over y. Since the problem is asking about dy dt when the ladder is 8 feet from the wall, we'll replace this x with an 8. Since we know that x is going to be 8, we can plug that back into the original formula for the Pythagorean theorem, giving us 8 squared plus y squared equals 144. And 8 squared is 64. And subtracting 64 from both sides of the equation, which then gives us that y squared equals 80. We take the square root of both sides, which is approximately 8.9. We can take this 8.9 and substitute it up here in place of y. Simplifying this fraction here, minus 8 over 8.9 is approximately 0.9. So at this point, the only thing left is our dx dt is given as the rate at which it's coming away from the wall. So our x in terms of time is just a 1. And this tells us that the top of the ladder is moving down the wall at a rate of 0.9 feet per second. Our answer is negative because it's moving down. And that's the final answer. In this next example, we're pouring sand onto a pile and it is forming a cone. And we're interested in seeing the relationship between the height of the cone and the base of the cone, with the height of the cone being labeled with the dotted line. The question states that sand is being poured on a pile at a rate of 100 cubic feet per minute. Find the rate of change of the height of the pile when the height is 10 feet. And for the purposes, we're going to assume that the radius and the height are equal. The given rate is a change in volume, so we have dv dt is a constant rate of 100. And we're asked to find dh dt when height is 10 feet. Our starting point will be the formula for the volume of a cone, which is pi r squared h over 3. And since we know that the radius is equal to the height, we can replace our radius squared with height squared. And height squared times height to the first power is height to the third power. Using implicit differentiation, we get, so we bring the constant to the front, which is pi over 3. We bring the exponent to the front, times h, reduce the power by 1, dh dt. Since we have to find dH dt when h equals 10, we have to isolate the dH dt, so all of this must move to the other side. We'll multiply both sides by 3 over pi first, which would then simplify. We then multiply both sides by 1/3, which then simplifies on the left to be 1 over pi. And on the right, 1/3 times 3 is just 1. Then dividing both sides by h squared, we get 1 over pi h squared times dv dt equals dH dt. And we have to find dH dt when h equals 10, so we'll replace the h here with a 10. And h squared is 100, so we have 1 over 100 pi. dv dt is given as 100, so we replace that. And then multiplying, we get 1 over pi. And 1 over pi is approximately 0.318 feet per minute. In this problem, we're told that we're inflating a balloon and air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Well, in this example, the related rates are going to be volume and the radius. We can express the volume as the change in volume, dV, with respect to time, dt. And that's given in this as 4.5 cubic inches per minute. What we're trying to find is the change in radius at the point in time when the radius is 2 inches. Now, in order to relate these two, we'll start with the formula for the volume of a sphere, which is 4/3 pi r cubed. First, using implicit differentiation, on the left side, we have dV dt, which is the change in volume over time. And then on the right side, we'll use the chain rule. We bring the exponent 3 to the front, and we reduce the exponent by 1. And then using the chain rule, we'll do dr dt. Now, just to point out, what I've done here in this section is I took the derivative with respect to r, and then I'm multiplying by the derivative of r with respect to t. Simplifying over here, I'm just going to have 4. Now, since what I'm trying to find is the change in the radius over time, I need to solve this for dr dt, so I divide both sides by 4 pi r squared. At this point, since I know the change in volume with respect to time is 4.5, I'll substitute the 4.5 in for the dV dt. And then simplifying on the left, I have 4.5 over 4 pi r squared. And I want to know what the change in the radius is with respect to time when the radius is 2 inches. So I'll plug this r value in for here, and r squared in this case be 2 squared or 4. So in the bottom I get 16 pi. And 4.5 divided by 16 pi is approximately 0.09 inches per minute. A conical shaped tank is being filled with water at a rate of 2 meters cubed per minute. The tank is 4 meters high and has an opening at the top of 4 meters. That's its diameter. Find the rate that water is filling the tank when the water level is at 2 meters. Let's label our diagram. So on the diagram, our opening is 4 meters, so the radius is 2 meters, and the overall tank height is 4 meters, and we want to know the rate at which the water's coming in when the water level is at 2 meters. So the two rates that are related are going to be volume and height. For the volume, what we're finding is the derivative of the volume with respect to time, and then we want to find dH dt, or the height with respect to time as the water fills the tank. So our starting equation is going to be the volume formula for a cone, which is 1/3 pi r squared h. And the problem that we're going to have is if we're going to differentiate this, we can't have two variables on this side. Now, what we are able to do is express the radius in terms of the height. By looking over here, we see that we have one triangle here And then we have another triangle that's here. And these two triangles share this angle, and they both have a right angle. Since these two triangles share two angles in common here, this angle, then all three angles are equal, then these are similar triangles by angle, angle. So I'm able to set up a proportion. Labeling this triangle over here, I know the height is 4, it's this big triangle, and the radius is 2. This one I'll just put R and H. And now I'll set up the proportion. Once I have the proportion set up, 2 is to R as 4 is to H, I can now solve this proportion by cross product. So I have 2H equals 4R. So I'm going to solve now by dividing both sides by 4. So now I have R in terms of H. So now I'm going to square the 2H over 4. So that gives me 4H squared over 16, which can be reduced to H squared over 4. And since this is the R squared term, I'm just going to replace this R squared with this term. And that can also be written as 1/4 times H squared. And then we have H squared times H to the first power. This becomes H to the third power. And simplifying the 1/3 pi 1/4, this would give us pi over 12 times H cubed. And now I'm in a position where I can now differentiate this with implicit differentiation, since there's only a single variable over here. So I bring the 3 to the front, I reduce the power by 1, and I have to also differentiate, so I have dH dt, since I differentiated h with respect to time. And then over here, the 3 and the 12 can be simplified with the h squared in the numerator. And on the left side, since we differentiated, this becomes dv dt. dv dt was given initially as 2 meters cubed per minute, so 2 meters cubed per minute. And in order to get what we're trying to find is h with respect to t, we're going to multiply both sides by the reciprocal of this. So on the right-hand side, once this simplifies, the only thing left is dh dt. Looking on the left side here, I know dv dt is 2, so we'll substitute that in. And simplifying, we have 4 times 2 is 8 in the numerator. And we wanted to find dh dt when h was 2 meters. So we'll substitute in a 2 for h here, and 2 squared is 4. And of course, 8 over 4 pi reduces to 2 over pi. And if this is on a test, this is usually accepted as the answer. If you were to actually divide 2 by pi, you get something in the ballpark of about 0.64 meters per second as your final answer.